this is my final applied AI project. It is a tool to help automate machine learning workflows where you're able to download a data set and it will auto visualize and make a machine learning model and then automatically deploy it to cloud storages like AWS. So let's start this presentation. Okay, the problem that I was trying to fix, or more like an innovation that I was trying to give to data scientists, is that data scientists, the main role should be to analyze data and find improvements. And some things like some repetitive tasks like downloading data sets, creating basic machine learning models, and data visualization can easily be automated to help data scientists really focus on being able to more look at improvements and trying to find insights to the data rather than doing repetitive tasks. And the idea the professor actually gave me was MCP. So MCP is an open protocol that helps applications to provide context for large language models. So what this basically means is that large language models have a extension, kind of like a hand that they're able to go use other resources. So large language models in general are only able to generate text and generate images or videos, but they can't actually access external tools like databases or cloud applications or being able to use APIs. But MCP is able to help large language models with that. It's like MCP is basically like a tool where LLMs can use, or like it's like a gateway for LLMs to be able to say like, okay, I want to be able to use this tool to use this API. So it gives LLMs a more context to your problem and gives it more tools to be able to access. Therefore, it gets a better solution. And it provides the large language model user interface as well for you to be able to work with while the MCP server runs in the background. So think of MCP as basically a server in a way. It's basically a server that's built for LLMs to use. Kind of like how apps use RESTful APIs. Large language models have something called MCP, where it's like a server for that large language model to use, and they're able to talk to it like you would use for a RESTful API. Think of the large language model as the client and the MCP as the server. So upon some prompts in the client, it'll go to you'll go to the MCP, and then it'll execute code there, and then it'll return the result back to the large language model for the user to see. So it's basically a relationship like you would see from an app to a RESTful API, or from a website to its backend, or from front end to a backend. In this case, it's from large language model to MCP. The only difference is that it's more automated. It's usually in a typical RESTful API to app connection. It's just a one-time request sending back and forth, but this time, after one request, it will use all tools possible to give you the best possible answer in return. So yeah, MCP is basically a server for the large language model to use to be able to access external tools. So with that being said, let's dive into the MCP workflow of what I built. So firstly, let me move my camera so you guys can you can see the you could see. Okay. So the first thing is data download. So we need to be able to download the data in order to start the workflow. So the way I've set it up is you can just submit a Kaggle link, and the Kaggle link will then be sent to this function. And this function will take in the Kaggle link, and then it will run through this function. So as you can see, it goes through here, and then it will access the data set, and it'll save it in cache. If the link is invalid, then it will return an invalid URL to the front end for the users to be able to see. But if the URL is valid, then it will use the Kaggle API. Like I said, LLMs are now able to access APIs because through these tools. So we could use the Kaggle API to be able to send in the link and download the data set. Then the data set is downloaded to a temporary directory, and then it is saved into a cache for further use. And then at the end, it is returned to the front end or the large language model for users to be able to see, hey, the data set was downloaded successfully, and then it'll output the shape, the rows, and the columns. And then on exception, it'll throw errors for the users to be able to see if they did submit a wrong link. As you can see here, it starts with the prompt. So the user asks or submits a link and asks it to do a couple of tasks. It downloads and saves the data set. if the URL is valid, and it downloads it because we need to be able to use it for the future workflows. And then it previews the data set for just a brief preview to confirm that the data set download was correct. So that is the data download. So we can move on to the next one, which is preview. So preview data is just as it sounds. It just looks at the data set like a little bit more in depth, so the user can confirm if they downloaded the right data set or not. So the data set's already been downloaded. So what's going to do now, it's going to take in the name of the data set it downloaded, and then it's going to return 5 rows. So it will just grab the data from the cache. And why cache actually specifically? Because caches are really quick, so we want quick responses in the front end. So caching provides like a 0.1 time complexity. So by cache, we can just quickly grab the data set for users to be able to use. So if the data set is not there, then the data set is not found. But if it is there, then it'll return the first 5 rows for the users to be able to view and preview, again, to confirm or just to look at the data briefly after download. So you can see the workflow here. So as you can see, after the download, Claude uses the preview data set to be able to download data and look at the first 5 rows. And then you can inspect the data set, and then obviously the result is the first 5 rows in the data set, granting there's at least 5 rows. The data set has to be relatively or somewhat large, maybe after 100 rows to be able to execute in this workflow. But yeah, this is the preview data set tool. It's just a brief inspection of the data set that users can be able to look at. So after the preview data set, we want to analyze data. So this is where we dive in a little bit more in depth. It's just a little bit of it's kind of an extension to the preview, but you can look at like other things like mean, mode, range, standard deviation. So what this will do is this will take in the dataset name again, and then it'll grab it from the cache. Then if it's not in the cache, it'll throw an error and send it to the users to be able to see. But if it does find the dataset, then it will describe the dataset, so provide a little bit more insights of the numerical and categorical columns for the users to see in the front end, and obviously, and then lastly, it converts it to a JSON to be a little bit more presentable for the front end to be able to see. And again, on error, I'll throw the error to the front end. So this is a little bit of an extension to what preview does, but it provides more insights like through like basic statistical numbers like mean, average, and so on. So again, if you look at the workflow, after it previews the dataset, it will start a base analysis of the dataset. So look for basic factors like min, max, and other things. And then we'll call describe to be able to do that. And then the user in the front end can be able to look at the basic statistical factors like mean, range, max, and min. And obviously the result is that the users are able to see these things in the front end. So that is the analyze data. Analyze data is just a brief preview of, not preview, more like a small insight on what the data is going to look like. So the next one is clean data set. So we need to clean the data set. Obviously, not all data sets are not perfect, so we got to be able to clean them first. So in this case, it takes in the name of the data set, and then we have a category called encode categoricals to true, as we want to be able to encode these categorical columns to be better for the machine learning later on, as we don't want any strings in the data set, so the model is better. So what it'll do is, again, it'll grab it from the cache, and then it'll check if it's there. If it's not there, they'll throw an error. Then it'll go to this try-catch statement, and then in here, it will iterate through the entire columns in the data set, and for each column, it'll check whether or not there's any null values that exist. So if a null value does exist, then it will check if it's a float or an integer, or if it's an object. So if it's a float or an integer, it'll grab the mean for that column and replace those missing values with it. But if it's an object, then it will grab the mode of the column and replace it. So after the missing values are fulfilled and the duplicates are also dropped, we then move on to encode categoricals. So this is where the categorical columns will get turned into numerical columns, and then they'll get replaced into the dataset. And obviously, it'll update the cache and return the dataset. So this is just basic data cleaning. It'll get rid of missing values and duplicates. So it starts off by grabbing the dataset, and it'll look for null and missing values. Then it will start cleaning the dataset by replacing the missing values with mode or mean, depending on the type of data. Then it will encode the categoricals, and the result is it will, for the front end, it'll be able to display what the new shape of the dataset is. So if any rows or columns were dropped because of the duplicates, then the data shape will change. So this is just an update for the users to be able to see what the data shape looks like now, what the shape of the data set looks like now. So clean data is just basically a setup for it to be able to use the machine learning model later. So next is actually visualized data. So visualized data, it does it before the clean data because we need it to we don't want the numbers to be, we don't want the categories to be encoded. So we'll do visual data first, but in the workflow I have it set up so you do clean data then visual data for the numerical columns. But typically when we give the MCP tool a prompt, it will either do clean data and then visualize the numerical, or it'll do visual data and then visualize the numerical and categorical and then move on to clean data. So those two are interchangeable depending on the context of the data set. So again, MCP is able to auto decide which tool it wants to use or which is the best. So if the data set's mainly numerical, then it will do the clean data first. But if it's mainly categorical, then it'll do visual data and then go to clean data. But as for the visual data, it's going to generate a histogram for each numerical column, or for each numerical column. So what's going to do is, again, it's going to take the name of the data set, and then it'll take the name of the data set, grab it from the cache, then it will select all the numbers, and then it'll say no numerical numbers found in the data set. If there's no categories, then obviously it's not going to be able to visualize. But if there is mainly numerical data sets, then it's going to go to map. It's going to start using the matplotlib library. It's going to enumerate through all the numerical columns, and then it'll do a subplot for each numerical histogram. So obviously, this does allow some useless graphs to get on there, like ID and like names, for example. So there's no easy way to control that other than being able to have like a specific if statement saying don't output the ID. But ID doesn't have to be the name of the column for all data sets. So that's kind of a challenge. So this just for every numerical column, it just outputs the graph, whether or not if it's useful or not. But we can decide. So in the front end, it'll actually be able to visualize like the actual graph, and the users can actually see it. So from there, you can just decide which graphs are useless and which graphs are not, and then go from there. Again, so before we start the machine learning, it's going to do the little bit of data visualization to be able to see some more insights. So it'll visualize the data, and then again, the result will be a document of the histograms that were generated by the matplotlib library, and then users be able to analyze that. So this automates the task of being able to just visualize briefly look at the visualization of data. Obviously, this can't do like complicated visualization graphs. It can only do the basic histograms or whatever data type I try to give it. So based off of that, we can only automate so much. So it just automates the basic histograms. Obviously, data scientists still need to be able to visualize other things or other types of graphs like box plots and so on. Again, this is not to replace what data scientists are doing. This is just to stop the repetitive, or help them like not do the repetitive tasks, and for them to focus on looking at more advanced analytics and in-depth analysis. So after visualized data, we need to transform the data set, because we need to prepare the data set to be in the machine learning model. So again, we want to better suit the numbers. The machine learning model likes those numbers better. So obviously for the strings, we will do label encoding, because we want to be able to turn those strings into numbers. Then we'll normalize the numerical column. So we want to turn the strings to, not strings, you want to turn the numbers to be better numbers for the model to be able to use, so it has an easier time training the model. So obviously the point of this transform data set is just to prepare the data set to be trained. We want the numbers of the data set to be better suited for the model to be able to train it. So obviously it's going to transform the data set. So if it's a string, it will turn it to it'll use label encoding. If it's a numerical column, you'll use normalizer, and it'll transform. And then the result is it'll tell the user that the data set was transformed, and it'll tell the final shape. And obviously after the transformations are done, it'll save it back to the cache. So afterward, we have the machine learning workflow. We can't see the top part. Okay, I'm gonna temporarily go here. So this is the main chunk of the code in the model. It's the most complicated to code, at least, because you have to take into account all types of other models. So basically, this trained model will take in a couple of arguments. It'll take in the name of the data set as per all the other tools, but it'll also take in a target column, because we want to be able to specify which or what's it going to train on. we want the model type, as we want to, there's two types of machine learning models through classification and regression. So we want to know which one we're trying to do. And then we have the model name. This is optional. They don't have to specify a model name, but if they don't specify a model name, it'll pick the default one, which is none. In this case, none is just logistic regression or linear regression. And then again, the output is a string. So it's going to, again, grab the data set from the cache, and then it'll check if it's there, and then it'll check if the target column that was provided is there or not. If the target column is not there, it will retry to find a target column that's more suited. So then after it picks up the data set and the target column, it will then check whether or not this is a classification. So I have it set up by default classification, but obviously you can change it to regression if you specify in the prompt. So if the model type is classification, and they'll check what the model name is. Obviously, if you don't provide a model name, by default it'll pick logistic regression, because or the model is a none. And so by default, it'll pick logistic regression if you don't specify the name. But if you do specify the name, then it will pick some of these other models that you specified. So random forest, SVT, K-neighbors, or decision tree classifier. The same goes for the regression. For the regression, if you don't specify a model, it'll pick the linear regression by default. Otherwise, it'll go to random forest regressor and decision tree. And then obviously it'll train the model and fit, and it'll predict. So after classification is over, it will do an accuracy score check and give the accuracy to the front end to be able to see. So the users can actually see what the accuracy of their model that it trained was. Or for linear regression, it will take the mean squared error and see what the mean squared error was for the front end to be able to see. So it will return the model that was used and the accuracy of the model, and then here it will return what model was used in the regression and then what the MSE was. So this is the main tool that's we use for machine learning. It's usually relatively quick, but sometimes it can take a while, especially if it goes into SVC. Linear regression, logistic regression are usually pretty quick. One of the time constraints actually for this tool is that since it's integrated with large language models, large language models have a timeout error. So after some time, it will just timeout error even if the code is still executing. So for tasks like what we're about to jump into next, which is hyperparameter tuning, if you do the hyperparameter tuning for too long, it will just do a timeout error even if the code is executing. Obviously, that's a restrict thing that they set up in the large language model that is out of our control. But I've tried to minimize the length of how long it'll take to tune. So obviously, let's dive into this tool first, and then I'll explain how I minimize the time for that. So you have the hyperparameter tuning. Again, you have the name of the data set, you have the model type, classification, regression, and then you have the optional model name that if you provided it or not. Again, grab the data from the cache, then it'll check if the target column is there. Once it checks that, it'll retrain the model, and then it will go through the same process as the machine learning model tool, with the exception, do some parameter grids. So obviously for logistic regression, it got parameter grid. For random forest, it's got its n estimators for 100 to 200. For SVC, it's got its C and kernel, and then K neighbors, it has the number of neighbors, and then for decision tree, we have the max depth. So based off of these parameters, it will start doing a hyperparameter tuning through something called grid search CV. So the grid search CV was what I had originally, but I've changed it to random search because grid search searches through all possibilities and the parameters, which does take a while. So this tool originally had timeout errors. Sometimes if the data set was small enough, it will be able to execute the hyperparameters, but I've changed it to the random search CV, so it has a quicker time executing, and I've also reduced the parameters so that there's less range to search. Obviously, this is a restriction of the large language model because they have a timeout, like a specific timeout set up. So hyperparameter tuning does clash with that timeout that's originally set up, but that can be fixed through some optimization through random search and reducing the parameters. So again, this is one thing that I will say it can't quite automate. It can do some hyperparameter tuning, but if you want full hyperparameter tuning, it just doesn't have the time because of the constraint in the large language models. But moving on, so hyperparameter tuning, it is able to do the basic ones. Obviously, it'll take in the model, and it'll improve the model using the grid search, which we've changed it to random grid search, and then for the result, it'll output like the best parameters that was chosen. So now we're approaching the last two tools. So the last tool is to save the model. Let me move over here. Come on, move with me. Move with me. There you go. Okay. So saving the model, obviously after we're done, we want to be able to use the model again. So one of the things I talked about for the solution was we wanted to we wanted to get rid of the repetitive tasks. So one of the repetitive tasks is just to be able to save the model or deploy the model. So at the moment, given the time of the project, I've only had the time to save the model. So what we can do is, after everything's over, it'll take the name of the data set, and it'll grab the model from the cache because we saved it into the cache, and then it will actually save the model into AWS. So in the AWS, it will first it will dump the model to a local file, then it'll upload that file to AWS. So we can save the machine learning models into a cloud storage for future usage, or you can re-download the model and then work on it in a different environment like Google Colab. But again, this is just basically this workflow sets up a base model for people to work with. So after that base model has been trained, it'll save it to your AWS S3, and then from there you'll be able to access and work with the model in other environments. Again, workflow is pretty simple. It'll take the name of the data set, and then it will save the model to the AWS S3. And firstly, you'll use the joblib to dump the model into a local file and then send the local file to S3. And then the result is that will tell them that it's been uploaded to this bucket on AWS S3 for them to be able to check. So this is one thing that paid large language models can't do. I guess they can't deploy or save stuff, right? So this is one advantage of MCP as we go to the last tool. So the last tool here is saving the data. So saving the data, so we save the machine learning model, but we also want to save the data. So I picked a database to save it in, and I think the most appropriate one was MongoDB, because most CSV files are in the style of a document, and MongoDB is really good at saving documents. So you can save the data to your MongoDB database. So again, it takes the name of the data set. It'll grab the data set from the cache, and then it'll check if it's there. If it's not there, then throw an error. Then it'll convert that that data frame to a list of JSONs, and that list of JSONs is then stored inside of a collection instead of a MongoDB database, and then it'll return which name or it'll return where it was stored inside of your MongoDB collections. So that concludes the end of the workflow. Obviously, now we can dive into examples that we've seen. So first, again, let's look at the conclusion of so again, this is the workflow. It saves the data to MongoDB, and the result will show them where it was saved. So that is the workflow of how the MCP tool works. I have slides on some examples, and I'll do a live demonstration at the end so we can see how it works. So again, so we provide them the link of the Kaggle. It'll download the data set, and I tell it to clean, transform, and train a classification model, logistic regression, do some hyperparameters, and then save the model to AWS S3 and save it to MongoDB. And then you have to specify target variable. So at the very least, you still have to tell them like which tool to use and which target variable. So you have more control over how to be able to go about this workflow. So after that, what it's going to do is going to use that download Kaggle dataset tool we talked about at the beginning of the workflow and download this Kaggle dataset, and it'll respond with, hey, the dataset's been downloaded with this many amount of rows, this many amount of columns. So this confirms the dataset was downloaded. So then the next one was preview dataset. So preview dataset will help you confirm whether the dataset was correct or not. So obviously it'll print the first 5 rows of the dataset. So as you can see, after that was downloaded, we can see what's on the first 5 rows, and we can see that the dataset was successfully downloaded. So we can move on to the next part of the workflow, which is data visualization. So data visualization will actually open up a window in Claude. So again, this MCP tool is connected to Claude. That's the easiest configuration for this tool. So Claude will just open up a window of the data visualization it did. So in this case, again, like I mentioned previously with the useless graphs, like this ID graph is pretty useless. But like the age graph, the trust BPS, the cholesterol, the CA, like some of these other graphs are pretty useful. So again, it'll provide a little bit of insights, but for advanced graphs, you still have to do that yourself. But you can briefly look at some of the things. Like here, we have this is pretty uniformly distributed. this is also pretty uniformly distributed. So we can like see these little basic ideas through these visualizations that it's able to automate. So this is an example of a data visualization it does. Nextly, it can clean the data. Again, so go clean the data. So it will clean the data with removing the duplicates, and it'll tell you what the new shape of the data frame is. So this is just to prepare the model for training. So not much here. It just cleans the data set, like as we mentioned previously, and it'll give you the shape of the new data frame afterward. Then you'll use the transform dataset tool. Again, we specified the CPU as the column. Then we normalized the numerics, and then we encoded the categoricals, and then it'll tell you the new shape of the data set at the end. And so this prepares the data set to be trained through the machine learning model. And then through the actual model, we can see that, heart disease classification and CP. So CP did change the target variable. So because we transformed the categoricals to, we label encoded the categoricals, the column names changed. So it's able to adjust and pick the right column for it to be able to train. So CP typical Enigma is the correct column after the transformation. So it's able to, so on error, it's actually able to adjust and pick the actual column that was supposed to be trained. So again, we got a pretty good accuracy this time with the classification model, accuracy 94.57. So great. Again, yeah, train the model, show you the accuracy. Lastly, not lastly, after this, it'll do the hyperparameter tuning. In this case, the model we picked was just a base model, logistic regression. So we had the best hyperparameters. I'll tell you what the best hyperparameters were for the logistic regression model, and it'll train the model on that. Again, random search, and yeah, pick the best hyperparameters. Then it will save it to AWS. So the name of the model that it trained was heart disease model.heart disease. So it saved the model as heart disease.pk1. So as you can see, this inside of this AWS, this is the AWS S3 bucket screen. So it saves the model here to pkl1, 850. Yep, there's the model. There's not much to it. It just saves the model to AWS S3 for you to be able to download and use it for the future usage. And lastly, it'll save your dataset to MongoDB. So it saved it inside of a collection called dataset heart disease, and then when you open the data, you can see that it's been accurately saved. And the ID looks a little funny because it transformed the dataset. But yeah, it saves the transformed dataset into into MongoDB for future usage. So that concludes the end of the workflow with the examples. Obviously, this is a summary it'll give you at the end of everything it did. So download the Kaggle dataset, clean the dataset, transform the dataset, train a logistic model with classification, perform hyperparameter tuning, save the AWS. And so it'll give you like a final report on what it all did. And that concludes the workflow for the entire workflow.